So we're now going to have Bob Dara take control again and talk to us about point source models, but this time we're going to address more in depth some of the issues with point source models, including the single and double corner modeling, distance and depth, which we discussed, and magnitude dependence. So here we go.
Thank you. Good afternoon. I'm going to continue with the point source model. And the first topic we're going to talk on is single versus double corner. And we're going to look at that with some spectral shape examples, both in Western North America and Central North America. So here's a very simple point source model. It's for a moment magnitude 6.5, depth or JB distance of 25 kilometers. And there's 1 and 2 corner shapes are plotted. Again, we're plotting spectral shape, so we're plotting spectral shape, so it's SA over A max, PGA. It's done for geomatrix AB, which is soft California rock, 550 meters per second, and the assumed kappa is 0.05 seconds. So here you can see the double corner model is lower in spectral shape at long period than the single corner model. And Gale proposed this model to somewhat address the overprediction at long periods. You can see from the slide earlier in the day, the point source model started to overpredict the data from approximately 1 hertz or 1 second to longer periods. The double corner model was meant to address that, and you can see here that it's lower than the single corner model over that frequency range. And now we're going to do a similar comparison against spectral shape, again for the same magnitude, same distance, and now we have to give a strike slip in geomatrix AB, and we're going to compare single and double spectral shapes to the spectral shapes from the 4 NGA GMPEs. So I have A&S as the solid line, Bohr and Atkinson, Campbell and Bezornia, and Cho and Young's all shown here, and they tend to cluster quite close to each other over most of the period ranges. The two models, the double corner is down here, and it basically falls it's a lower limit for the GMPEs. The single corner is here, and again you can see that it basically overpredicts the results from the ground motion, from the 4 ground motion prediction equations, again from about 1 hertz out to 0.1 hertz or 10 seconds. So again, we're showing 4 Western GMPEs and a single and double corner model in the West for strike slip faulting, magnitude 6.5, which is right in the middle of the data set that went into the GMPEs. Oops. All right. This is from Nahanni, which is either a Western or an Eastern earthquake, but it's in Canada. It was recorded on a couple rock sites. Again, we show that the 50th percentile is the solid line coming through here. The 2 dashed curves are not 16th or 84th percentiles. They're actually the minimum envelope of the spectral shape and the maximum envelope of the response spectral shape from the rock sites that recorded in Nahanni. So again, you have minimum and maximum. Here's the average of the data going through, and there are 2 models that are shown. Is there a way to do it? Oh. Well, I want to move the slide up a little bit. Oh, there it is. Okay. And then again, there are 2 models that are coming. A Central Eastern U.S. single corner model and a Central Eastern double corner model based on Atkinson's work in 1993. Okay, well, the double corner model is down here, and it's basically somewhat near the minimum of the data for Nahani. The single corner is up here, and again from about 1 hertz out to 0.1 hertz, it's near the upper part of the data from Nahani. So for Nahani, it's going to be a challenge to model this with either a single or double corner, at least looking in spectral shape. Also at high frequencies, we have here using kappa of 0.006, we're over-predicting the data from these rock sites. We can get a better fit out here by increasing kappa. Okay. This shows the same, shows a couple other comparisons. So we've taken off the maximum and minimum spectral shapes from Nahani, just left the median curve, and we've added Atkinson and Bohr's 2004 curve, which comes through here. So it's a little higher than the double corner model from about 1 hertz on, but then it's a little lower in through this frequency range. So those are kind of 3 models that are available to fit data in the east in spectral shape. And some people consider Nahani an eastern earthquake or a western earthquake, just depends on, it did occur in Canada. Right. Okay, this is Saguenay, and everybody believes this is an eastern earthquake. Magnitude 5.9, and we're using just the 2 closest stations because we're looking at spectral shapes, so stations 16 and 17. Again, we have the 50th percentile of data in solid line and the maximum spectral shape and the minimum spectral shape. And again, we show 2 curves, the CUS, Central Eastern U.S. double corner and a single corner. And in this case, neither model does very good at shorter frequencies. The double couple is again lower than the single corner, and this trend here, as some people described, is the spectral sag in the Saguenay data. So the fact that the Saguenay data drops below both the single and corner model has been, some people think there's a deficiency in energy and response in Saguenay in this intermediate frequency range. Again, similar to what we did for Nahani, we show, again, just the median of the data, and then 3 possible models for Central Eastern U.S. We have the single corner, and this has a stress drop of 120 bars, the double corner with a stress drop of 500 bars, and the Atkinson 1993 curve here. And again, we fit the data reasonably out to maybe 3 or 4 hertz, and below that, all 3 models are higher than the spectral shape, between like 3 hertz, and in this case, the data goes out about to half a second. This is somewhat a summary from earlier on, but these are a couple issues for Central Eastern New York. One we talked about this morning is looking at stress parameter. Is it a function of moment magnitude, top of rupture, and mechanism? We see some of those indications in the west, and can they be transferred to the east or not? That's a topic for future data acquisition and analysis. And then the spectral sag, we're comparing active versus stable continental regions using large magnitude sources. This is something Jack Boatwright's been looking at. This may help identify the spectral sag. And if it does exist in Jack's or other people's work, we'll need to define the frequency range and depth of the sag for modeling purposes. And this is where I thought I was going to start the afternoon talk. So we're going to talk about large magnitudes now. And some of this will be a little bit of a review. So we're going to look at point source models. We're going to look at 3 main attributes of the point source model. One is saturation, and there's 2 ways you can get saturation. You can have your stress parameter be a function of moment magnitude. That'll lead to saturation. Or you can keep your stress parameter fixed and use a fictitious depth, which is a function of moment magnitude, and that'll cause saturation in the point source models. The second one is the far field slope or geometric attenuation curve. And the third is the distance metric. What's the appropriate distance metric to use? And we talked a little bit about this morning. Do you use JB? Do you use top of rupture? Do you use a fictitious depth? Do you use hypotential depth? So we're going to look at all those 3 points in a little more detail in this afternoon part of the talk. All right. First couple slides, we're going to see saturation due to magnitude-dependent stress parameter and a moment-dependent far field fall-off. So here, a single corner model and variable stress drop. And for magnitude 4.5, it's 160 bars, which is this curve here, the lower curve. And for magnitude 8.5, we have 70 bar stress drop. So here we're varying stress drop as a function of magnitude. And there are 2 places to look in epicentral distance to see, one, saturation. As you're at very small epicentral distances, the difference between each of these magnitude units, which are increasing by order 1, decreases as you move to higher magnitudes. So that's the saturation effect that comes out of the model. In this case, by having stress drop vary as a function of moment magnitude. The other thing to look at in this model is at large distances, out here, the far field slope is changing. It's steeper for lower magnitudes and tends to flatten out as you move to higher magnitudes. So those are both 2 attributes of the point source model. Okay, this one we're looking at basically peak ground acceleration versus distance. Now we're going to look at it in spectral acceleration versus frequency. On this one, you want to look at high frequency, PGA, and again you can see the effect of saturation as you move from lower magnitudes, magnitude 4.5 to 5.5, 6.5, 7.5, 8.5. Again, in this model, the stress drop is decreasing from 160 bars here, 160 here, down to 70. Now we're going to look at a different way to get saturation in the point source model, and that's using fictitious depth with constant stress parameter. And again, you're going to find we also have magnitude-dependent far field fall-off. Now this slide is a little busier, and we have essentially the top 5 curves are the same range of magnitudes, 4.5 to 8.5, with stress drop constant. Okay? I'll backtrack a little bit. This is again a one-corner constant stress drop model for the mid-continent, and we're looking at PGA. So we have ground acceleration versus epicentral distance. And then we're including, in this case, a fictitious depth, and you can see at magnitude 4.5 that the curves are basically the same. But as you move up, these curves start to drop down below the curves without saturation, without using fictitious depth. Okay? So in this case, the top curve, this is for magnitude 8.5, 120 bars. It drops from here down to here with the use of fictitious depth. All right? The 7.5 drops from here to here, the 6.5 from here to here. And by the time you get down to 4.5, the use of fictitious depth has very little impact on this implementation of the point source model. Okay, this is looking at spectral acceleration now as a function of frequency. Same data, just plotted versus frequency instead of versus epicentral distance. Again, you have the 5 models with constant stress drop and the 5 models with constant stress drop and fictitious depth. So here again for 8.5, you see the effect of saturation along this axis. Oh, and I forgot to point out, in this model, you also see the effect that far field, the slopes are different for magnitude 4.5 than they are for magnitude 8.5 out here. It's flatter. Okay. So that ends that portion of the point source model. Now we're going to look at the distance metric. And we usually use JB distance, and we can look at that with magnitude-dependent depth and depth to largest disparity. Okay. So here's some modeling for a large earthquake for Denali, and this goes back somewhat first part of the talk. There are 2 curves shown here on the model bias. One again is the point source, which is the dotted line. the point source is the solid line, and the finite fault is the dashed line or dotted line. And again, you can see that from about 1 hertz on, the point source has a negative bias or is over-predicting the data for the Denali earthquake at 22 soil sites, whereas the finite fault does better at long period, but potentially a little not quite as good at high frequency through here. Now, we showed this slide earlier. This is looking at the closest site, Denali Pump Station 10. And again, you have the data in solid line and a couple models, a point source model, which is in the dotted, and a finite source model, which is in the dashed. And you can see the fits here. We're using a very generic soil profile for here, just 270 meters per second. So with a better soil information, we can improve the fit at high frequency or the changing kappa. But out here at long periods, we see that this model, which is the point source, overpredicts, and the finite source model predicts actually quite well the longest period from 5 on, and both models tend to underpredict for this one station in this frequency range. All right. So these slides you've seen before, but I want to talk about a bit more a bit more detail on the distance metric. So we're going to look just at the 1 GMPE, the 3 magnitudes, the 7 distances, and for soft rock. This one, we'll look again at Bohr and Atkinson and see the effect with distance. We're using a JB distance here of 1 kilometer for M5, M6, and M7. And down here, we're at 10 kilometers for M5, 6, and M7. And 2 curves to compare, and this one is a solid and a solid dashed line. So this fit or inversion argues that in this case, especially as you move out to larger and larger distances, that the point source model fits very well Fourier amplitude spectra generated from the GMPEs over a wide range of magnitudes and distances. So 3 sets of magnitudes and 7 sets of distances. So again, this is just a summary. So to summarize what we've seen, the point source issues for CNA are what is the range of stress drop or stress parameter at a large magnitude? There's some ways you may be able to get at that using historical data. You can look at intensity data. From that, there's a correlation with moment magnitude. You can also look at liquefaction, which can give you some idea on stress parameter or stress drop. And then you have questions on how, in your model, you want to build in saturation. You can either use that as having a stress parameter be a function of moment magnitude or fictitious depth h, where h is some h prime, and then an exponential is a function of magnitude. Okay. We've seen earlier that at least in the West, there's some data that suggests that stress drop is a function of magnitude, top of rupture, and mechanism. But there's definitely coupling between stress drop and fictitious depth. And then in the East, there's the spectral SAG. So you want to comparing, and Jack Boatwright's doing work in this area, and define the spectral SAG in the East, which is prevalent in the Saguenay data, especially for the 2 closest in sites. And one thing that would be helpful would be an update of Gail Atkinson's 2-corner point source model, so we can take care of event-specific properties. Currently, the distribution of the corners is fixed as a function of magnitude. It would work better in our modeling if somehow we could scale with high-frequency scaling or variable stress drop, and also some way to parameterize the intermediate frequency SAG using some sort of upper corner FA, FB, and epsilon, which would describe the depth of the width. So you describe both the width and the depth of the SAG, right? And then this is for tomorrow. Yes. How far?
Let's start on the 2-corner.
Simple 2-corner model. Oh, Well, real data, okay?
This is Gale's.
Yes, this is Gale's two-corner model.
So, can you explain how the second corner is being determined, or what is the?
Gale determines it's fixed. In Gale's model, the corners are determined as a function of moment magnitude. So we plug in 6.8, and out comes the corners. Yeah. So in that way, it's fixed.
In looking at, so in comparing to Nahani, whether it's Eastern U.S. or not, if you had changed the kappa, so increased it, that would also change the shape, right?
Yeah.
So if the kappa went up to, say, 0.01 or 0.015 or something to match what the observations are, your long period shape is going to go up, right? From your model.
PGA goes down, your long period shape will increase.
So
this will push out this portion. So you can push this into here. Right.
So I'm just trying to, so if we were to match this part, then this thing here would move up closer to where the data are. Is that correct?
Correct.
Okay.
But we have to move away. Right now we're using a generic Eastern North America kappa from the EPRI value of 0.006. Now we know a bit more about these sites. So if you move away from the EPRI kappa, you can get a better fit at longer periods. But there's a trade-off in the modeling from moving away from that center value of 0.006 seconds. Yes?
And we're using shapes to judge two-corner versus one-corner. Is there a reason for showing it as shape as opposed to showing it as response spectral values? Would we be seeing the same thing or coming to the same conclusion? You know what I mean?
Yeah, there's a whole concept, the shapes versus absolute.
Right.
Yeah. The nice thing about shapes is I
don't want you to have to look at me when you...
Oh, okay. The nice thing about shapes is that it pegs the high frequency. My cell phone is off.
Your cell phone's off?
Oh, yeah.
Could you say that again, Bob?
Sure. We use shapes a lot for looking at spectra when we're just looking at one site. And some people like shapes, some people don't like shapes. And there's reasons for using it. But one thing it makes is the comparison at the high frequencies the same. So you can see what happens without varying both PGA and it tends to cut out one of the apples in the equation. But yeah, you can look at this in the absolute world too, and you're going to see similar trends. But your point is right. If we increase kappa, we can get a better fit to this.
To the shape there, right?
Right, but we're using standard C, E, and A values without monkeying around with the model. I mean, we can do better fitting.
Right, for a site that is close to Eastern U.S. conditions, but may have higher kappas in Western Canada than Eastern U.S., right? Okay.
Because it's a big magnitude.
Dave, in looking at these one-corner versus two-corner models, do you look at shapes, or are you used to looking at absolute levels, or how do you deal with it? Yes, please. I think what this comes back to in what Bob is doing, how do we want to have data presented? Do we need to see both of them? Do we need to is one preferred over the other, or?
I've never really played around with shapes, so I don't have a really strong opinion. But the difference between the single and the double corner model is longer periods. And what I'm wondering is I'm concerned with shape because they're pinning it at very high frequencies. And as you pointed out, the kappa can then propagate back and change the apparent shape. But if you had normalized it at a a lower frequency, like 5 hertz or something like that, would that sort of then get rid of some of that problem and would perhaps be a better way of displaying the shape? I don't know. I really like the idea of looking at the absolute rather than just shape also, because I think that's very important. In addition to shape, right.
But at 5 hertz on these, it happens to be they're all about the same, right? So this one,
true.
We would have got
that would have been.
So then it comes down to sort of, if we go to Saguenay as well, that's the next one. Is that?
That just has more models. That has 3 models on it. That's Saguenay.
Saguenay. All right. So our so the Gale's model as published does not capture the big sag in Saguenay, right? Or so to speak.
I don't know. Yeah. Makes it easy to remember.
And what you indicated was we could be estimating for these kinds of an event what second corner would have been required to match these? I mean,
if we get it.
What modifications would you have to make to Gale's model to get it to look like Saguenay?
Right now, Gale's model determines the second corner based on magnitude, whereas magnitude for us is fixed, but we, as shown in this example, vary stress drop. Well, we vary stress drop. So here there's an example, Central Eastern U.S. at 120 bars and 500 bars. But the corners in Gale's model are at the same place because they're based on the moment magnitude of 5.9. So that would allow us the flexibility.
I think
stress drop events.
Well, what we're getting at here is, do we need to be looking at a different formulation for the double corner model that's more flexible, or Dave?
My memory is that Gale's double corner model does not have delta sigma, the stress parameter, as a parameter. It's strictly 2 corner frequencies that are a function of moment magnitude. And so you don't have an additional stress parameter. On average, the stress parameter in her model is equivalent to a Bruin stress of like 120 or something like that. So it could be that another formulation that adds that a little extra flexibility would be useful.
So that would let us, one way, fit data better, but also then start to look at the parametric variability of what that parameter would be. Right. So I think in our list, I've lost, Christine, can you get back to write something down here? That's okay. Gale, are you there? No. Okay. Sorry. So one concept here is to take the 2-corner model and just generalize it so that we actually have a stress parameter term in the model, as opposed to she has magnitude, which has basically fixed stress parameters, and then you would have whether the position of the second corner is also a parameter or fixed is something we need to think about. You don't want too many parameters.
I don't think you can have all 3 completely independent, because in the shape it's going to be hard to do.
Right, so there'll need to be some constraints so that we're not allowing too much flexibility, but we want to be able to get an event term in there, right? This is essentially what we're getting at. Even the first corner. Is that the first corner is also fixed, right, Dave? In the current formulation of the 2-corner model. So we need it so at least we would have a source term that may change the whole spectrum up and down, and whether or not we want, Bob talked about the 2 frequencies and the depth of the sag is the complete parameterization, but that may be too much freedom. Bob?
Bob Herman, with respect to the two-corner model, it was created to match the Saguenay earthquake data set, which had data at shorter distances than the Nahanni. So you have to be very, very careful that whatever you do, you must fit the Saguenay data. And you cannot arbitrarily change parameters without botching it up completely just because of the functional form that she has right now. So that's my only caution.
But if it was derived to fit the Saguenay data, why doesn't it have shapes that match here?
These are the two closest sites, most important. These are the two closest sites, and Saguenay data goes out to 400 or 500 kilometers. And the bulk of the data, so it fits the bulk of the data out at larger distances, but doesn't fit the close-in sites, which may or may not be of most interest. I mean, if we're going to go out to 1,000 kilometers. Oh, yeah. Well.
It's John Evans here talking about the Saguenay data. And what I want to say is I just don't want to get down into the weeds. This is not a proponent discussion. But it worries me it's getting off track at this point. The problem with the two-corner model is it's designed to fit mostly the down rupture data. You're trying to compare it to the back azimuth stuff. Furthermore, the Saguenay rupture in this direction consisted of a large rupture going away and a superposed small rupture coming towards it. So it's actually got two earthquakes in one spectrum.
So we're not talking proponent models, but we do have to decide what we're going to do. And so if I say that we will look at one of our needs is to generalize in some way the two-corner model with the caveats that Bob Herman noted that we don't want to just take her form and just shove it in a variable stress drop. It probably needs to be re-derived a bit in terms of its approach. Okay, that's something we'll have to leave as a task to deal with a more flexible two-corner model that has an event term in it that we can consider. Yusef.
Well, if you do it, you have to validate that.
So Yusef, not coming up to the mic, said we have to revalidate the model, which is correct. Anything we use has to go through the validation process, but we need to set that we're going to have the suite of models that we want to check. And one option is to say we will check Gale's model as is versus a two-corner, a generalized two-corner model that has a second source term in it that can be optimized. Dave?
It's even a little bit more than that because, her particular model is essentially an additive thing. There are two terms, and it has quite a large sag in it. But there are other two-corner models that don't have such a pronounced sag, just depending on the formulation. I mean, Bill Joyner has one, for example, where there's an intermediate slope. And so, you have to make some decisions about that as well.
So that's something that we actually should be thinking about here. If we're talking about this kind of a model, it seems to me it should be a simple parameterized model such as two straight lines as opposed to a sag with an amount of dip in it. But is that, Bob, you're looking at Bill's model. So maybe taking Joyner's model then and okay, so Dave said it looks at the two terms multiplied together rather than being additive. So let's put on here that in one of the models that we should be pushing through the validation would be a Joyner type two-corner model. Is that a way to put it? Okay. All right, I think we're through the two-corner model part. Any other comments on two-corner models that we need to consider? So as Yusuf said, whatever we talk about here has to be put through our validation process. And we don't want to do too many, but we want to capture something that we think is is going to be potentially a viable model. Paul, anything else? Paul Spudich? No? Martin? No other model? Okay. Your next topic was, so that was our end of lunch,
Yep.
right?
Saturation.
Okay.
Saturation either is a stress parameter fixed with fictitious depth or stress parameter variable to function magnitude. So these are just the outputs from single corner variable stress drop models in Central Eastern U.S.
Did all of these have a magnitude-dependent geometrical spreading, or was that just on one of them? You know,
All these.
all of them do. Okay. A question that I had was, so I get to ask the first one. When you went to the term here, okay, so that depth, or you had the saturation versus non-saturation here. What's being used as the distance metric? Because if you have the small event is at depth, is the depth of the event here and not just epicentral distance? What is being put into the point source distance for the magnitude 4.5?
There's two parameters. There's the epicentral depth, and then there's the fictitious depth, which comes out of, out of this form. Now,
Use the microphone.
oh, it comes out of this form, but I forget what its constants A and B are. So that gives you the fictitious depth.
It's not zero.
Right. Walt, is that correct?
If you've been using hypocentral distance, I would have said, okay, yes, those things are going to sort of hypocentral distance with a fictitious depth of 0, then they would have been the same. That's small magnitudes. Is that right, Walt? I'm kind of lost there.
Walt, so the fictitious depth is added only for magnitude 6.5 and above. It's just a magnitude-dependent depth. So for 4.5 and 5.5, it might be 6 kilometers. 6.5, it might be 8 kilometers. That would be the H prime. Don't have it there.
I think.
Which slide do you want?
So you've got an H prime, you have a constant depth that's like 6, and then it increases as the fictitious depth part.
Right, that would be the H prime.
6.
Yeah, the magnitude dependent.
And then this term increases that. Okay. And that's just calibrated empirically, or how is this part calibrated?
Yeah, empirically.
From the validations that you had to do.
Actually, they're based upon the GMPEs. So it's trying to get the same saturation that's built into the GMPEs. So A and B are determined from the GMPEs, NGA GMPEs.
As we went to the eastern United States, does H prime stay the same? Or does that become a region? Does that parameter have to change?
Yeah, it gets deeper.
It gets deeper. Okay, but we would keep this the same because you have nothing else to calibrate against. Is that right? So this H prime may go to, say 15 or whatever, where you had deeper events. but then you would have this term, whatever the A and B values were from California.
They get carried over.
Okay.
So it's two. This is just two approaches of getting saturation built into the point source model, which by itself doesn't have it. The constant stress drop one is for those who need comfort and who have insecurity with a magnitude-dependent stress drop or stress parameter. What comes more naturally when you try to model previous ground motions or GMPEs, you're forced to a magnitude-dependent stress parameter.
Okay, so these are two alternatives for getting saturation.
Right.
And your preference is a magnitude-dependent stress drop.
That comes from?
We would typically use both in a hazard analysis and then argue about weights between the two.
So this slide earlier shows magnitude-dependent stress parameters from the GMPEs. So as magnitude increases, stress parameter decreases. That's one way to get saturation. As Walt was saying, you can also use fictitious depth. And they give very similar curves that look very similar.
So in setting the runs that we're going to have done for the point source model, we need to decide what to ask Walt to run, whether we're running both of those approaches, just the fictitious magnitude-dependent depth approach, or just the magnitude-dependent stress drop approach. Part of when they start to do the calculations, we can get the whole big suite of calculations and let's say, again, essentially pick out the combinations of magnitudes and stress drops that, with weights that give us a magnitude-dependent stress drop that we think is appropriate, or the range of what those values are. Ken.
So Walt just implied that basically you get the same results either way, but I'm thinking in close maybe, but isn't the depth model is going to go away with distance pretty quickly? But shouldn't the stress drop model transfer to larger distances? So shouldn't there be an impact, say, at moderate distances as opposed to close distances, or am I misinterpreting what might happen?
Walt Silva again. Ken, you're exactly correct. The effect on saturation at PGA or with response spectra is a bit different between the two. So it will have different distance effects and different effects on the scaling with magnitude and with period. My own feeling is that the magnitude-dependent stress parameter is a more natural way to do it. It comes right out of the model. Well, I think Bob showed the response spectra with the magnitude-dependent stress parameter compared to the suite of response spectra at different magnitudes, compared to the same type of plot with the fictitious depth. And the effect of the saturation is different over different period ranges. I don't know, do you want to look at it again?
I guess my point is that if you use, each of those models to try to invert the NGA, does one of them perform better than the other, or in essence they're just the same? I mean, you're almost acting like we could carry these forward as two separate, equally valued models, and I was just wondering, you probably use both of them to try to interpret, or do you mix the two, interpreting the NGA model to get the best fit? I'm not quite sure how you did the inversion on the NGA.
We're lining up here.
Guys are ganging up against Bob and I. We've just used the magnitude-dependent stress parameter in inverting for the NGAs. We haven't looked at the goodness of fit between the two different assumptions. There's people who apparently don't believe that there should be a magnitude-dependent stress parameter, so we just put this model together with a fictitious depth to address that concern and show some weight of that model in the hazard calculations or evaluations. Next.
I think it's a combination of the two. I think the magnitude-dependent depth is really capturing the effect of finiteness of the fault. That's what I think, and then that's going to capture, shows in close, it's going to have an effect, but then overall, there's probably a magnitude-dependent stress parameter as well. So I think it's actually two things. And I think that to capture the effect of fault with finiteness using a magnitude-dependent depth means that you can use the point source at close distances, hopefully, for finite fault calculations. That's my feeling at this point.
I just want to comment that Dave and I are in violent agreement.
All right, so part of this is how do we move forward today in terms of saying what do we need to get done? In terms of saying we need a suite of point source models just implemented, capturing just a range of distances that are plugged into the point source model and magnitudes, okay, and stress drops so that you have a whole suite of them, produces all of the data that we end up needing, whether we interpret that magnitude 7 where they plugged in 15 to be at a distance of 1 kilometer, or whether it's at 5 kilometers later on for the hazard calculation, is something that we can adjust as we end up running them, right? So for today, the key is just what models do we need run? We're talking running a single corner model. We're talking about running a double corner model, two double corners or one double corner. I'm not sure if we're going to end up running Gale as well as a joiner model. And those would be the sets that we would ask them to implement for us. And then later we can work through in our proponent model evaluation whether we're interpreting these as saturation due to fictitious depth or saturation due to stress drop. Okay? Bob, yeah, you'll have to come tell us, come share with the rest of the class.
Well, Somerville, Paul, you had your hand raised.
I'm sorry, Paul? Both of you guys, come on now. That's okay, together. So we'll keep things up.
Okay. So we're almost done.
Oh, I was just asking Dave the question whether Gale had done, that's the new model from Atkinson-Bohr is finite fault simulation, which produces some differences from Atkinson-Bohr 95, whether she'd done anything to look at changing her formulation to match what the finite fault was producing. And the answer was, she does a lot of stuff that I don't know about. So we'll have to ask Gail whether she's looked at any modifications to the original formulation for the double corner in result of all the finite fault simulations she's been doing.
Okay, and trying to recast the net of how this fits in this workshop. we're trying to define the range of applicable or reasonable models we're going to consider, right? So that's why I know that some of you think the discussions went too much in depth, but if it leads to the fact that we need to consider one model to run or two, depending on budget, and I see Youssef's face is getting long, but you know, that's part of the, yeah, so that's, we just need to get that resolved, and that's one of the questions we'll have today and tomorrow. Do we cover the range of simulations? Do we cover the range of parameters we'll look at? So although it may seem convoluted, we're getting there. Paul, last comment?
Yeah, Paul Somerville. In a study done a long time ago for EPRI, we compared the source durations of eastern North American earthquakes and other analogous stable region earthquakes with, looked at the scaling of source duration with seismic moment, and we found it was decreasing stress drop with increasing seismic moment, in agreement with what Walt and Bob are finding in the western U.S. But, sorry, I got that wrong. The western earthquakes behave the way Walt and Bob are describing them, decreasing stress drop with increasing seismic moment. But the eastern North American events and other stable region events did not have that condition. In other words, they had constant stress drop. So in that case, looking at source duration, it seems as if what happens in the west didn't seem to transfer to the east. So it may not be reliable that whatever holds out here works back there.
There was a lot of noise, but I think what I gathered from that, Paul, is that you're saying that from your experience with the stable continental region, that dependence on moment or magnitude was not as strong, right? No dependence. Okay. There was just a lot of noise coming out. Okay. I think that we're done on this session. We have exposed a few of the problems with point source models, and we have, I think, identified potential other simulation methods that we can use. So now we will move on to talk about finite fault. Yes, that's today. So we had an RFP that was sent through the simulation working group to have people submit proposals to use their model to do some finite fault validation. And 4 people were funded, and plus we have a couple other projects, other simulation, including the FinSim method that's going to be looked at. And Yewa Sang is going to give this presentation now. Yewa? He's gone. So I'll start the presentation. No. I don't know. I don't see him. Well, he was here a second ago. Okay, he's coming back. Sorry about that. Yeah, we're good. Take your time. We have 3 minutes ahead of time. You can walk slowly. Okay. Yewa Sang, sorry.
You have a point?
No, please use the mouse.
Oh, just use the mouse here? Okay. I'm going to summarize the method considered for the finite fault simulation. We have a total of 6 methods going to be used for the finite fault simulation. At least for the validation exercise, the 6th method has been selected. Some of the methods, like the 3 in red, has been used for the West, the NGA West, and those are used to do the simulation and use those simulation results to constrain the shape of the ground regression formula.
some additional methods that's developed after that as UCSB and Kimolson's method. And the method by Gil Atkinson and his colleagues, this is called XSIM. It has been quite popular. A lot of people use it back east. So we want to put this one also in the validation exercise and in the simulations afterwards. Some of the methods has been implemented in the SSHAC computation platform or SSHAC broadband computation platform. That's a URS, UCSB, and Awesome. And the DENS method is in the planning stage to be included in that platform also. In the following, I'm going to summarize each of those methods. But in essence, we can see this is the observations. And if we know pass it below 1 Hz, we can do quite well using waveform modeling. But above 1 Hz, it's difficult to fit wiggle by wiggle, and we have to look at the envelope forms and have to use a stochastic approach. So many of the methods in the following summary will have some kind of hybrid approach for the low frequency and the high frequencies. First, look at down the move. Oh, okay. Okay. First, the URS method. This is a hybrid approach to broadband ground motion simulations. For frequency above 1 Hz, you can see that there is a kinematic representation of heterogeneous ruptures on finite fault as slip amplitude, rate, rupture time, slip functions, and so on, and wave propagation using 1D FK or 3D finite difference approach. Okay. So right? So that's for frequency below 1 Hz. For frequency above 1 Hz, it's using a extended Bohr's method 1983 with limited kinematic representation of heterogeneous fault rupture. That's a slip amplitude rupture time and conic average radiation pattern with some stochastic phase. The wave propagation was modeled by simplified Green's function for 1D velocity structures, mostly just geometrical spreading from ray tracing and impedance contrast from the source to receiver. Both have used consider the site amplification and also nonlinearity based on VS30 of Campbell and Borognier 2008. Somehow this mouse. Okay, and this is how this method generates kinematic ruptures, and this is a smooth ruptures, and then I use some kind of a non-linear or some kind of random phase, and also K-2 4R to generate this slip distribution on fault. And this is for the low operator earthquake, how it transferred the wall and all slip distribution from strong motion inversions to their models. That basically is the smooth part and also the generate high frequency part using the Ma and Barossa. And then then they add up the rupture time, which have a dependency on the local sleep amplitude. And later on, I will show that the UC Santa Barbara have a different way of doing this, but from their dynamic rupture scenario computations, they did some statistics, found out in their exercise or in their models, they didn't see the relation between the rupture time and the local sleep amplitude. And then they also have this rise time. It's proportional to square root of the local sleep amplitude. And then this is rise time as the sleep time functions. And they also introduce a rake, this kind of minus 60 to plus 60 degree from original obtained from or specified or obtained from inversions at lower frequencies. And then they kind of, for the high frequency, there is some kind of modulations, and using Franco 95 to rescale the high frequency to target main shock moment and also rise time. And here we sort of noticed for the West they have 50 bar stress drop, and for the East have essentially double the stress drop. And also for the there's also depth dependent rupture velocities. It's like 80% of local shear, only about 50 to 60% above 5 kilometers. This is also the corner frequency that's for the West, and there's a difference between West and the East. West essentially doubles the constantly doubles what in the back East. And this is one of the examples, and shows the comparison between observations. That shows in black, and red is the synthetics. You can see this directivity effect to the north of the Northridge ruptures, and those are stations in the basin. So overall, the amplitude match quite well, and but there is in the basin there is some over predictions at the low frequencies, but maybe just to this particular site. And that's how they match to with at different distance. So PGA, PGV. Those are the bias and standard errors across the wide frequency range from like 10 hertz to about 5 or 7 seconds, and it's doing quite well. And this is a Walls method. This is a random vibration approach. And in this method, the magnitude of point source kind of distribute, kind of also it's a finite fault, and divide them into small subfaults. And subfault events, use a magnitude 5 to build up those subfault ruptures. And stress drop, you have a 60 bar on average, but they do have for the 10 bar for fault depths less than 2 kilometers. So they too have a consideration for the shallow depth ruptures. And for the rise time and the ship velocities, that's a relation put there, and also the ship velocity is 62.5 centimeters per second, with some kind of variations given here. And rupture velocity is 0.8 of local rupture velocity, local shear velocity, and geometric spreading and attenuation that using O and Hermann's, and sub-events Q. They use layered Q or use frequency dependent Q, and that's also that's the ray. This geometric spreading is from ray tracing. Amplification, that's 1D or inclined 1D vertical or inclined SH, and they have equivalent linear for soil, but also have a non-linearity built into the process. This is only applied to the horizontal component. The output is time series. It can also be spectral acceleration or peak values and so on. And there's some kind of safe distribution built into this process. It's another K-2. It's more of a K-1.4. That was from early April study. Mai and Broza, there's more recent studies showed -2. So that's some difference here, but Wall had mentioned if I want to change to that, have to reduce the constants here. So it just still keep the same form. This is one example they did for 6 earthquake, 6 finite fault rupture comparison. There's a bias, and this is standard errors, and it's doing quite well actually, but this low frequency still have a little. I'm not sure it's under or over predictions. And this all got into in the final discussions about the low frequency part for the random vibration approach. And this is my method, a composite source approach. Basically assume large earthquakes is a superposition of small sub-events, ruptures, and this the radius and the number of those sub-events follows the distribution, parallel distribution given by Franco 1991. It's essentially the Goldenberg-Richter distributions. And this is how we do it. We generate the sub-events given magnitude, and then distribute those one randomly on the fault for scenario simulations, or we can actually locate those support locations to match the waveforms of given earthquakes. And I also did scaling for the stress drop. So from linear interpret from 0 to 5 kilometers, and from there keep a constant stress drop. And also currently consider there's a 1D FK method to compute the wave propagation, but we do consider the shallow layer complexity in velocity structures, 1D velocity structures. And also include scattering from small-scale heterogeneities. And in a recent update, I include non-isotropic scattering. It's basically a full type of scattering, and it matches the observation quite well. You can see this is one example. And there's a Wales, Nevada earthquake, and you can see from close vision to large vision, we predict the common coda decay quite well, and also match the early post. This is envelopes. You can see it predict the broadening effect of the observation quite well. And we also consider nonlinearity effect. This a side amplification, kind of build them together using nonlinear, true nonlinear computations. And those side amplifications based on VS30, we use Daswell 2. It's a kind of improved Daswell 2 to do the computations. This is one example for Northwich too, and you can see this is the observation synthetics for the horizontal component, and those are the same stages showed for Paul Somerville's case, and that's up to the north. You see the strong directivity effect, and then back to the southern stations. We do not do well for Tazana, but for other stations, like even for some of the basin stations, we are not doing bad, and at large distance, we capture the long durations very well. That's the coda waves. We did a prediction for this one. That's a rock wave about selected 15 stations out. And some of them, most of them, not used in the validations. And we compute the bias and standard errors from those stations, and we're not doing bad actually. It's PGA and PGV. And this is the fourth method is UCHB's method, and this is a flow chart of this method. This uniform distribution of rupture velocities around some range of, and the truncated Gauss distribution for slip, and beta distribution for rise time, and this is the rupture, this rise time functions. Later, the recent update have changed this one to more of truncated Kirchhoff formulas. And they use the Q and the S velocities, and using, if it's a 3D case, using finite difference simulations, and or for high frequencies, using 1D, and then combine them to also consider nonlinearity and so on. This is how they did for the slip. That's the truncated Gaussian slip distributions, and this is the rupture velocity average around 0.8, and that's the rise time. And the recent update is from the dynamic simulation. They found that the Kirchhoff type, truncated Kirchhoff type, match much better. That's how they do this functions. And they're also building some correlations between sleep and rise time. And here is an example. They found sleep and rupture velocity have zero correlations. And also peak time and so on. For high frequencies, they used this Pataki 2000 to run either randomize strike deep and rate, and this is how they do it. And then for 3D they use finite difference and so on, and then also for high frequency they use a 1D model, and they have to combine the 1D and the 3D. That's the way how they combine the two. And the fifth method is Olsen's method, and this method combines the low frequency and with the high frequency, low frequency deterministic synthetic with high frequency scattering operators. And for side effects, they consider soil structures and also non-linearities. And scattering effect is for inhomogeneity in Earth structure at Earth scale. Basically, that's specified by scattering Q and the intrinsic attenuations. And this is how they actually do it. And this is scattering functions, and computed using Zheng et al. 1991 and 1993. And this is their source time function. They convolve the two to come up with the high frequencies. The source time function, it's not clear on their recent paper how they did it, but from previous conversations, what they did is that they used Mai and Broda to come up with a SIP distribution, then using isochrone method to compute from there to compute the source time functions, and then convolve this one with the scattering functions. And this is how they do the matching, and that's a low frequency and high frequency, how they put them together. They also say that they introduce phase matching. So that's, I'm not quite sure I know exactly what they did, the phase matching, but this is the diagrams. My guess is that they match the arrival time of S waves. And this is their one example of how they validate against Northridge, Lander, Norm Prada, and so on. And this is a Northridge examples with bias, standard errors. So looks they are doing quite well. And this is the final one is from Atkinson that they call the X-SYM. And this is has been used by many people. The method is quite simple. It's basically Bohr 1993 approach to generate this is random variation of shape, this shape function using Bohr 1993, and to come up with this waves from the subfault. Then they bring it to frequency domain and normalize to 1, and then multiply this one to by the source, path, and the site to come up with the actual radiation from that subfault, and then they sum up all to at the station to get final solutions. And normally for those approach, they have problems with the low frequency because the phase is random. They tend to cancel each other. So Motazden and Atkinson 205 introduced dynamic clonal frequencies. It's kind of conceptually that says the rupture propagates the clonal frequency of the seismic one will change to lower values. Usually, what it's done is it happens naturally. You just when you sum up those subfaults, they naturally produce those kind of lower clonal frequencies. But in their ways, they kind of did it in some ways we'll discuss in next few slides. But that's the way they kind of try to push the method to low frequencies. They have some quite interesting consequence. So that's the method, and I was asked to give some pros and cons and advantage, disadvantage. Instead, I will just put into a comment on issues. And those common issues are like URS and Zhen's method, and also PGN Wall's method. Consider those kind of depth dependent, either rise time or stress drop, or also have some kind of or rupture velocity scales. And the few of the other methods didn't consider this, but maybe Rob has mentioned from Ullman and Scheer, they didn't find the global data there is any dependency. But I look at that paper, it's actually they have very little data for the shallow, for the top 5 kilometers or depth. So that's not we're not sure about there. But this is mostly motivated from some of the recent surface rupture events. They generate not as much high frequency as those kind of buried ruptures. And US, UCSB, Zen, and Olsen have a variable rupture velocity sub-events, rake angle, rise time, some kind of relation between rise time and the local sleep, and has this kind of a wave number squared fall off in sleep distributions. UCSB have considered dynamic rupture characteristic for sleep time function correlation among rupture speed, rise time, and local sleep, and so on. And other methods can also build those in, but have not been put there explicitly. But UCSB's method has built them there. And Zen and Olsen's method have this scattering function for high frequency. That's the issues about the matched filter for the hybrid approach. That is like around 1 hertz. That's how they kind of match the two. And the question here is it's amplitude match and phase match or wavelength match. And I heard that UCSB used some kind now using wavelength match. But this are essentially 2 different approach, and we're just using this kind of amplitude match is the best way. So that's not quite sure. Some of the phase match just try to match the arrival time of those S waves or some other waves, and or could be more complicated way of doing that. So that's we can talk more about it. By talking around, there's some concerns about from this random vibration approach about low frequency. I talked with Wall, and he say his method don't have that problems because probably he has a positive low frequency or static radiation from his subfault. So maybe that problem has been solved there, but there's some concerns with the Axim method. Essentially what they did is the propagate from when wave propagate out and finally finish, that's the last rupture sub-events radiate the low frequency that match that will be scaled to match the moment of the final rupture. So that maybe that's a better way. Rob have showed me one of the paper. They actually have some modification to this approach, more physical ways, and we can probably discuss about that. Other comments that USB are also using green function for 1D, 3D wave propagation, and this method uses 1D wave propagations, but can also extend to 3D. And those methods naturally include body waves, surface waves, LG particularly for the east, that's for large regional distance, and RG and so on. And the random vibration approach uses 1 over R for body waves, 1 over square root of R for surface waves, but do not naturally have those kind of dispersing characteristic of the surface wave and the LG and RG and so on. those are the methods I have explicitly considered nonlinearity soil response, either using some kind of parametric way or actually compute using finite element or finite difference, compute the true nonlinearity response of the soils. And URS, USHB, and Olsen's method will include in the SSHAC computation platform, and Len's method is planning to include. We have submitted a proposal at the SSHAC request. We're kind of hoping all the method will be implemented in SSHAC computation platform, so it can be simple for the future simulations, but it's not required at this stage. And for the import, essentially for all the models, it needs fault geometry, hypercenter, P, and absolute velocity, Q, and Fmax, saturation moment, site conditions based on VS30, site kappas. And for URS, USHB, Olsen, and then they have a SIP, rise time, rupture time distribution, and also have some correlation among those source parameters. Has considered variable rate and strike. This just helps you randomize some of the source characteristics. This model, this is not explicitly have the SIP there, but the SIP distribution was defined by sub-events, a stress drop with random distribution on the sub-event locations. The Walsh model have a SIP distribution, SIP velocity, sub-event stress drop, and so on there. The two random approach have to what I understand is have a constant rupture speed, and the rupture time and the corner frequency was defined by some formula. So that's my summary of this of those methods. Welcome to your comments.
Okay, so the intent here was to cover the finite fault simulation methods and try to see if we capture enough diversity in there to capture, again, reasonable alternative models. Norm is preparing a slide right now. Although Yewa went into details about each method, which is useful for us to understand, everything related to soil nonlinearity is irrelevant since the simulations will be done on hard rock. So I'm just a parenthesis, we'll keep that out. Yeah, we'll come back to that. Just no, we'll see about. After more. Further down. Oops. Oh. Did you put it on top by accident? That's it.
Yeah, okay.
Mm-hmm.
So, Just to get us back on the focus of what we're trying to get through today in terms of what do our data needs. We talked about, we have those 4 different procedures that we're going to be looking at for generating ground motions in these single corner, double corner, point source models, the hybrid empirical, which we haven't talked about today because we will wait until the point source models are done, which it builds upon. And then Yewa was going through the finite fault simulations. So I wanted to summarize what our basic approach was in looking at models to use. And one was we weren't looking for methods that are under development or are still being, we only considered methods that we considered ready to go, okay, and that have had some previous checks on them. So they've done some of the previous validation. We're having each of these methods go through a consistent set of validations. So there's 7 validation earthquakes that we have selected, 4 from western U.S. earthquakes and 3 from eastern U.S. earthquakes that will be used. And once this is done, the simulation working group will give a grade to these simulation procedures of a pass, no pass, either or pass, fail grade, and then select the methods that we'll use to go forward with the forward modeling for generating the whole suites of cases. What we wanted to talk about are the 6 methods that we selected, capturing the range of currently working or available models that are out there for finite fault simulation. I put them in a couple of broad categories, and you can correct me, Yewa, if I've got them right or not, but we have 2 of those basically stochastic finite fault models. That would be the Pacific Engineering and then the Atkinson models. 3 of the models have this hybrid approach of a long period deterministic calculation with a empirical or stochastic high frequency part, being the URS model, the UCSB model, and then the Olson model as well. And I apologize if I'm using names versus institutions. Those 3 models, as Yewa indicated, they're all using Green's functions, but they're all on the SKEC broadband platform. One of the reasons for us preferring that is it gives us a way moving forward that you can actually do some QA on these types of simulations. We can repeat them. We can be sure that what the inputs were to the model was the way that we intended it to be, and checking the outputs in that sort of way. So part of what we're looking at doing is actually having people other than the modelers implement the models and see if we can get the same results out, which will be an interesting exercise. So that putting the models on the broadband platform we consider a real plus. And then there's one that I put yours in a sort of separate category, Yewa, that it's not a hybrid approach, right, because you do all frequencies together. It's not stochastic, but you have your stochastic part being the random location of the sub-events, if that's right, with Green's function. So the key discussion question that we'll talk about right now is, do these 6 methods capture the existing, the space and approaches of sort of ready-to-go finite fault simulation? Is there another one that, yes, Dave? Yes, you have to come up here.
First of all, is Rob Graves in the second one? It's not actually being used, right? But he has. Sorry. Okay. It's not. Yeah, that's right. USGS. Thank you. Anyway, and then I happen to know of some other. I haven't read the papers, but there are other people in Europe who've done things like this. A guy named Galovich who has a model. It's a K-squared model. I don't know if it falls in those categories or not, but I think it's worthwhile doing a little more literature search to check. Okay.
Some of the methods actually already have the K-square built in, like Kim Olsen's and URS. I think also the UCHB and also my method also have those characters built in.
I'm just saying that we shouldn't just consider U.S. things. We should be looking worldwide and see if perhaps there's something from other countries where people have developed models that have something different than we have, okay? And that's the only thing I'm saying. Also, if you're going to use the XM model, I don't know if you're aware of my paper in 2009, but I've made some modifications to that to correct some of the problems that it has. So you should be aware of that. Yeah.
So, as brought up, there are other models that have been used in the Pegasus project that were used for suites of finite source simulations that we didn't receive RFPs from or proposals from to deal with this, but I think we need to check that we're still not missing really a credible model out there that is not captured in these kinds of approaches that we've got. I don't know if any of you have specific experience or with those other existing models. We don't have, for example, Iracora's method and so forth. There are quite a few other models that are out there, but the key question is, are we missing something fundamental in how they're doing their calculations? Any comments on that? I don't know, Paul, if you have any ideas of are we really missing a key approach here, or are those more of flavors of the same type of an approach, I think is what we need to think about.
You mentioned Japan, and there are indeed methods being used in Japan. Okay. Professor Irakura developed a recipe for ground motion simulation, and it's used in several contexts. One of them is making ground motions for earthquake scenarios throughout Japan for a set of scenario maps. And then secondly, that method is used at nuclear power plant sites in Japan. Actually, I helped develop part of that. The characterization of earthquake source parameters that we use in the US model is all very similar to what is used in the Irakura recipe, because I developed that, the beginning part of that. But since then, there have been further elaborations and developments on it. In Japan, they initially pushed the empirical Green's function method as far as they could, but I think they don't use that method very much anymore because it's just really hard to find suitable empirical recorded, as it were, Green's functions from small earthquakes to sum up to generate larger earthquake ground motions.
Closer, but to the side.
Okay. All right. So I think that empirical Green's function method may not be commonly used in Japan, but it is a method. I think a very hard method to use in the central and eastern U.S. because of the lack of suitable recordings, I would guess. So I think mostly what they're doing is similar to the hybrid methods that were described by Yehua, where you calculate a synthetic seismogram at low frequencies and then a stochastic seismogram at high frequencies and combine them together. So I think that's what the state of the practice is in Japan.
Do you think that the values would be very different? If we took, say, an Irakura simulation and for example, one of yours, have you tried to do the same simulations as Irakura's to see how the results compare?
No, we have not done that comparison. I just add a few more comments. I think that the use of simulation methods is a lot further ahead in Japan than it is in the United States. As I mentioned before, it is the standard method for generating ground motion time histories for the evaluation of nuclear plants in Japan. So I think it has gained much wider acceptance in Japan for that particular purpose at least than it has in the United States.
Paul Spidich?
I don't know if there's a canned empirical Green's function method available, but one of the advantages of considering an empirical Green's function method for the East is a lot of the methods, at least, for example, the ones that use computed Green's functions that you've seen here, they're going to have their hardest problems at long distances because they can't model the propagation properly in a heterogeneous crust. You're interested in high frequencies. So they all basically boil down to the stochastic method. And I'm wondering whether there might be, on the other hand, there might be, for long distances and long distance simulation, there might be some useful recordings of real earthquakes that might be used in the eastern United States at long distance for an empirical Green's function simulation, where you could actually have the long-range propagation correct in a certain period band. So we might want to give some thought to whether there is room for an empirical Green's function simulation for special cases in long-distance propagation.
So one of the issues that we have to address, particularly in the TI team, is what are we going to do with these finite fault simulations? And what is our real intended use of them? So I'll start out, and then I'll like to hear what the rest of you have to say about this. So don't take off just yet, Paul. That I think the focus is really allowing us to use finite fault simulations to check how we are making the point source stochastic model, or what it's coming up with in close, such that if we needed to have that either magnitude dependent stress drop or depth dependence that we've just been talking about can be calibrated off of some of the finite fault simulations, or at least be shown to be consistent with that. My thought is that at longer distances that we will just be using primarily the empirical type of data that Bob had shown to set geometrical spreading terms that work out to 1,000 kilometers and not try to take our finite fault simulations out to those kinds of distances. But I'd like to hear what you others are thinking of. What do we do with the finite fault simulations? What's their role?
I agree with you, Norm, that we should use them as a way of checking on the point source things. And I also agree, I'm basically agreeing with you, that also for the more distant things, it's whatever the geometrical spreading and Q functions that we get from whatever empirical data we have, and we just build that in. And that's very flexible. Like the XM, you said it was 1 over R. It can be anything. You know, it could be 1 over R to the minus 1.3. So I agree.
I don't know to what extent the close distance ranges will be important to you, but of course the issues of directivity and pulses and long period response and intermediate period response is the place close to the fault where I really expect the finite fault methods and the stochastic methods to have big variance. So clearly, you know, checking these things close to the fault will be really important.
Please come over. In the meantime, I just have a little comment. based on experience. We have these RFPs, and we know at least of a few people who are aware of the RFPs because they communicated with us, but they decided not to have a proposal. So what do you do in that case when you think a method could have been interesting, and so some are easy to run, like the XSIM. I think we could just get someone to run that, but that's an issue. That's a critical issue. Yes, Dr. Bakostov?
My name is Alexander Bykostov. I'm former professor from Russia, and unfortunately I'm not famous in this auditory, and like Walt told me, it is my biggest problem. So I have 5 points to say. The point number one, my major is fracture mechanics, and I was working 25 years for government of Uzbekistan in Russia, and I developed all simulation for finite elements, for finite faults, and for faults with many segmentation. In early 80s, Vladimir Greiser was checking my results, was checking my program, and he is very competent in what he was doing in early 80s. So I did a lot of projects for industry, for mining industry, for gold mining industry. So I have some tools, and I have a choice today to demonstrate it post-position norm, what we have right now. If it will be useful, we can share this, or we can start working for you. It's up to you. So it's what I would like to say. We have also analytical solution for 3D finite rupture propagation. And the main reason why it was not included, because I messed up with something. I not presented in time my publication, and it was some issue without financial support. But what I would like to ask, if it's possible, we will run your simulation, if you agree, for free, of course, because we was not funded, and we will see what will be in the end. So it's my addition that we have one more model, and if it's possible, we would like to put it in consideration. Regarding all these 6 methods presented here, what my suggestion is that it's very difficult to follow all assumptions. We all know that assumption is very critical. Can we just ask everybody who participated, this is 6 teams, if each team will put assumption on 1 page, 2 page, what's the main assumption in the method which they developed? And then it will be clear, assumption A, B, C, D. And the reason for this assumption, because now it's very difficult to figure out. The second point, it's a lot of when you set up the fault, I think the main reason to set up the coordinate system. If you set up coordinate system and you set up all the station location, then you need to set up your sleep function. And if you have sub-events, we go through all this problem before. For all people, or maybe for each team, it should be shown how oriented the fault system. The main fault system is connected. Where the origin, where the fault starts, and how displacement vector oriented or velocity of sleep oriented in this coordinate system. Then you will have a lot of coordinate system related with sub-events and so on. So this is not clear from this presentation. Okay, I will show. The next issue, I have a talk with some people who involved in shake table experiments, and they asked me, it will be very helpful if output will be presented like displacement time history, velocity time history, and acceleration time history. Because for some reason, people who do the shaking experiment, they need displacement. People who do the energy analysis, they're using the velocity time history. And of course, acceleration time history should be presented.
Let's try to keep the topics related to NGEs. I agree with your general concept of having different time series. We already have an objective with NGEs to follow that. We'll try to keep this focused.
So The vector of displacement has three components, and it's big issue how these three components are oriented. If you would like cut at your parameters, let's consider only one slip. But if you have a combination of slip in different direction, it should be properly set up from beginning. And also, in some cases, you have tension. For normal faults, it may be tension component. So three components of displacement should be set up in like input file. And issue related with green function. The green function is from notebook. If you know the green function, then you can solve the problem. If you don't know empirical green function, why we are talking about the green function approach? And like Paul say, it's big issue right now with green function. This is what I like to say. Thank you for it.
Thank you. Hello? Oh, sorry, there's a mute here. So one point that I think that is coming out is like the clear description of the assumptions and what the parameters are. And this is something we're addressing. And actually in the RFP, each of the modeler had to explain what is fixed. So that includes assumptions, how it's going to work, and what are the variable parameters. And that's one thing we're looking at as well. I want to bring quickly just a side note. On Thursday, there was a slight change in the agenda. We're going to print it and have it available to you tomorrow. On Thursday afternoon, Ralph Archuleta will go over the validation plan for finite fault, kind of in a summarized way. It's not finalized yet, but we'll go over these issues and all that. So, so that summary of parameters and assumptions is in there already. Yes, Ralph, please come over.
So I wanted to come back to not clear yet between when we talk about the finite faults and empirical Green's functions versus, what they offer. But in the finite faults, there are a couple of things that are offered that are not offered in these point source sort of approaches. And one of them is that I think it's going to be critical when we look at the long distance, even though we may not get it completely correct, but the LG wave is a big factor in the east. This is a crustal reflection. And I don't know how these models that have that propagate into a homogeneous half space, the fact that you get, 1 over r to the 1.3 or 1.2 or minus 1, whatever it is, the thing about it is that the LG wave is not this wave that basically says, well, it's just some amplitude that's propagating. This is a wave that basically is a wave packet that is due to these crustal reflections. This is something that I think that you're going to have either empirical Green's functions, or you're going to have we're waiting for, obviously the path effects group to give us the, crustal structures, but at least these can be incorporated into these finite fault models. Because it's not taking into account, now, if it doesn't play a role, it would be interesting. I mean, if you're only looking at an amplitude, agreed. It could be like that. The other thing is that the point source models are misleading in some ways, at least my interpretation of them. Okay? Because when one talks about a point source model, it is not as if there's a single point source that represents that fault. There's a single point source for a given station. So when we saw pump station 10 today, the Denali fault is not represented by a single point source. It's a single point source to represent the ground motion at pump station 10. Is the same point source used for the same strong motion stations that were at Susitna over on the western boundary of the Denali fault? Or is there another point source that's moved over there close to that station? In other words, is it a single point source? In seismology, when we talk about a point source representing, let's say, an earthquake, you choose it, Northridge, and we take this and you will find inversions in the long period range. When a person talks about a point source, they mean that point source represents the ground motion for all those stations that are spread across the world, a single point source, not a point source per station. And so the point source approximation may work when you're comparing it with with these regression models, these GMPEs, because when you look at them, there's one distance, there's one magnitude, and they really do represent, in many sense, a point source representation for a given station. But when we're talking about if we're going to have to match data at many different stations with a single fault, will we put a point source for each station, or do you put a single point source? In other words, it's not clear yet. I'm sitting in the back and I keep getting confused as to whether or not that really is a point source, or is it multiple point sources?
I think we can answer that. It's multiple point sources.
Thank you.
So that's clear. That is, we're trying to find the equivalent spot to put a point source such that we get an answer out that appears to be correct. So that there is no single spot that we have a point source, and that's used for all stations. Each station gets its own location.
But suppose we have two nuclear power plants that are separated by 20 kilometers in the east, and we have an earthquake, okay? Now the question becomes, do you have a different ground motion for the two different power plants, even though there's one earthquake? I mean, you move the point source so it's closer, or do you really represent, is this earthquake, how is it going to be represented?
If this was a future earthquake, and it was an extended source, we would have two different locations of the point source to calculate the ground motion at each power plant. Sure.
So it's very difficult to make the difference at some point between discussions that lead to a decision or an assessment, if we covered the models or not, if we go in proponent discussions, okay? I'll ask everybody to try to think of that when they present their point or their issue. We're not going to judge the models here. We only need to consider which ones are going to be used, and if there's one that should be used that we totally missed out, then yes, a little bit of proponent or opinion, stronger opinions are good, but yes, please try to keep that in mind. Thank you.
In response to Christine, I'll try to be quite brief. I see that I have only 24 minutes. No, in response to Ralph, the PSHA itself takes care of those multiple point sources, because the distance you put in is the minimum distance to the rupture. And so that's where you put the point source. So it is an ugly procedure, but it gives you the right answer.
So let's, as we said, avoid proponent model discussions today. It's very difficult because that's what most of you do, right? You say this is the right model. Let's get back to what we're trying to get through before we take our break here. In our finite fault models, I think we have heard that there may be some other models we need to at least look at and make sure that we're not missing a key feature that they're using. I believe from the TI team's point of view, the large distances we will take care of with the empirical observations. We want the LG waves as they exist in the east, and the best way is to take the kind of data that Bob Herman showed, where we've got it out to 1,000 kilometers, and we can basically use that as our base case and come off of that for the modeling. It's really here, finite faulted are intended for near fault effects. I think, and Paul pointed out, if there's directivity and things like that, yes, we want to make sure that we're capturing at least the variability that we would get from finite fault simulations that may not be captured in what a point source model would give us. Is there anything in addition, in particular, approaches that you think that are ready to go, not that are almost ready to go? Okay, so really, this is not the project for fine-tuning models. This is a project for evaluating existing models. Pass fail, you're not allowed to go change them and say, now I know what to do. Okay, that will be in 10 years when we do this again. You can come up with your revised version. Any other one? If not, let's, almost made it, Paul. You need to come up here, I'm afraid. Even if it's short.
The answer is money, right?
Exactly.
So the answer to my question, how do we make sure we capture people that, so yeah, the answer Paul is proposing to encourage other people who would like to participate is more money and more time. So it's just, that's the solution. Okay.
There is, I will point out, separately being funded through SSHAC, solicitations of methods, new methods that can be implemented under the SSHAC broadband platform and tested. But that's different than what we're doing. That's a more basic science program, and that's where we should be developing new approaches.
Okay, so I think we're allowed a little break. I know I need one, at least a mental break. And on here we had, that we can take 15 minutes. Oops, that's the wrong day, so it looks like a long break. Yeah, we have 15 minutes, but we're on Tuesday. Okay.
So
we're ahead of time here.
Let's take a break until 3:30 because we need to finalize our summary here, and we can pull it together and come back here 3:30 and go through the summary of what we've had today. Are they fundamentally different? That's really what we're trying to find. Is there something reasonable? I don't need another deviation of, hybrid approaches. I don't need that's the approach that we're going to I think we're going to try to bring another one along. Well, yeah, and I mean, there's a bunch of them. We didn't get any. That's different. All of these models do. They all put in a hypercenter some none of the point sources. So the first two don't. The only reason we're talking about is the double corner being modified. If anything, it's trivial to do. These others all the complicated. As soon as you start to change something, it's really a big deal. Yeah, we have a curable direction. That's all this is. Point source. Which way this approach is going. Right. But our plan here is that these methods will be generating their activity. Our basic model is going to be what is probably the double corner. Crank out a building adjusting on that. Maybe the finite fault. Hybrid empirical tells us create a range. That's my guess. Yeah, well, I think the single corner is not going to work, right? You need source finite. The single corner gives us a shot at the source finite. Or next. Go all the way to the top. It should say like some, yeah, so read through this. is a shortened version.
Oh, what's your reference for that?
Yeah, but I think if you're going to put data needs here, it's look at, you could just say evaluate duration data in addition to point source model. I would just say no. That's really for tomorrow. When we talk about the stress drop. Paul, that's for tomorrow when we talk about stress drop distribution.
Yeah, we'll talk about that more.
Yeah.
Look briefly.
All right, let's get started.
Okay.
All right, please take your seats and we'll wrap up, I think, a bit early today. We'll get through, depending on how many comments we have. We'll start at the beginning.
Are we sure?
All right, what I'm going to do is not encourage a lot of additional discussion. What I want to just run through is what I think are the summaries of what we're taking away from today, and the key issues on comments will be, did we miss something on these topics, okay, as opposed to other issues? The topics being, what are we doing for reference rock, what are we doing for kappa, and the issues of what sort of point source models do we want to run, and which finite source models are we running. The inputs to those models are tomorrow, all right? They're not on open for discussion this afternoon. So Reference rock, we said it should be applicable to a range of velocities. What exactly that range is, we're going to have to work out, but it's going to be something broad enough that it will capture typical rock sites for the eastern U.S. so that they won't have to adjust off of that. We will, with that, have to have additional variability that's added to the simulations to capture that effect of having a range of VS values. Okay, and we noted as well in selecting where our reference value that we're going to start with, there ought to be a good reason to move off of what's been in use in the past, just so that we can make easier comparisons with the old ground motion models and not make small tinkering changes that aren't compelling. For site factors is going to be an issue for us. We need to have these at several, at all the locations with observed ground motion so that we can correct the data. We had topography-based models to look at. Other remote methods, Eric, I think that's correct, had talked to me at the break and said he has a method that was used at other eastern U.S. sites, so we need to talk to him to make sure we capture that. Other possible methods, V/H ratios, receiver functions, and another mentioned to me during the breaks was the quarter wavelength method can be inverted from the observations, and that's been done on with the Swiss data. One issue we always have with anything on the bottom is that when we're using the recordings themselves to invert our site terms, there's a bit of circularity when we then use them to look at the resulting variance. So we want to make sure ratios and things are better approaches for that. All right, kappa. So there's a lot of discussion on that. Again, not a single kappa, but the kappa should cover a range, a reasonable range of what those values are. That range has to get defined. But it, again, should be the range of typical rock sites such that adjustments off of that value are not needed in the application of the model. Kappa variability, again, will be built into the rock ground motion. Its effects will be built into the rock ground motion model. And we then also need to have some work done here on the bottom to get at constraining that variability, updating, for example, the work Walt had talked about from California sites. We'd like to go instead to eastern U.S. sites now and really pull out what that range of kappa value is for hard rock sites. And then when all of it's said and done in the middle there, when we do the simulations, we're going to pick a single rock, shear wave velocity, and kappa that will be used for the simulations. And again, correcting for or adding additional variability to the simulations to capture the range for both VS and kappa that we need to capture.
I have a question.
Yes.
So that VS rock is the reference rock that you're doing?
It's the same thing. So I didn't put down here, but the decision is reference rock and simulation rock are all the same thing. Okay, so we're not going to change it. And I think that's a good decision to avoid more confusion down the line. All right. Point source model. So some of this is just some comments that are not details. One issue was to make sure that the forward and backward parameter use, so the validation and the intended forward use of the model needs to be consistent. That is, we want to make sure depth or distance definitions are all consistent, using things that, what should we have here? Walt uses H. Okay, so I shouldn't have verified the variability. Christine, what was you had typed that one, I think. Holy cow.
I don't know what you were thinking, but I typed it. So, what's your question?
Where it says, need to clarify variability, norm proposes a...
yeah, exactly. Yeah.
So, I'm sorry. So what we are charged in moving forward with the validations is to keep them as simple as possible, such that we're not having a lot of additional parameters such as slip distribution in depth or asperity location that we would have to randomize in the application of these models. Those types of features will be randomized in the finite source model. So we're going to have them keep the point source model simple in its validation, and then it's simple in its forward application as well. Okay. Issue will be, can we get some further data on epistemic and aleatory parts of stress drop? That is there trends with depth and so forth, and style of faulting that we can pull out. Along those lines, they're suggesting we look at some of the recent work. This is what Ralph had brought up on depth dependence of stress drop, and so we will see what those data are showing, and that there may be some additional earthquakes that we could use. When we're looking at prioritizing our database expansion, if some deep events are going to be more important to get out stress drops, or let's see, at least having a range of depths, we can prioritize some of that in adding any of the additional data that will be added. Okay, and again, we'll keep things simple in our use of the models in the forward sense. This was just for our two-corner model, really what this should be. That the simple way to do is that we will be looking as well at Joiner's approach, so that we have the two terms multiplied together, and we could have an event term that we bring along with the two-corner model, and be able to basically look at variability of that event term moving forward, as opposed to just the single fixed model that's in Gale's current model. And this is where we ended up our last part of our discussion, that we have the single and double corner models that we just talked about, and that the finite fault models, we have these 6 that we are considering, and really, from what I heard in the discussion, the key method that's missing is the empirical Green's function method. And I think we need to think about if that needs to be added in, and if it's feasible in what we've got available from our data in the East to use as empirical models. So, with that summary, is there something that you think was agreed upon in terms of reference rock, reference kappa conditions, the way that we're going to move forward with the point source validation and modeling, or the finite fault simulation methods that is not captured in this brief summary? You need to come up here.
I think it's nice to add the shortest slide about data needs for geotechnical working group related to generic soil profiles and so on, that you are collecting the data at different sites. You showed, Yusuf, you showed one slide, but it's not reflected here. Data needs for geotechnical.
Can you pull that up, Yusuf? If there's something here that we haven't.
So this item was not officially on the agenda because you guys are working on it, right?
Yes. And what I was asked to put it in.
Yes. Okay. Yes, because of the for the station. Yes. Right. The VF of the station. Okay. 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 But you guys are currently working on a database, right?
Yes.
Okay. Just want to clarify that. Albert, the king of data.
It is not part of our rock ground motion model.
Yeah.
Is that correct?
Correct.
We need to know that what kind of data they're collecting, and if it's sufficient, it's not sufficient, whatever their plan. Otherwise, when we are going to hear from users about geotech data needs.
Well, okay, I think maybe I'm wrong here, but I think that since they haven't really focused on it yet, the first time they're going to present their database is going to be where we present the final database, which is in workshop 2. So I guess, but I mean, do you have issues that you have identified already?
They come in workshops, they said we collected that kind of.
We just didn't start, right? So, I mean,
No,
yeah.
we have.
Started, but not.
No, we don't have.
Yeah.
Let's try to get ourselves focused again. We have in the SHAC framework, we are developing rock ground motion models. Okay? This project is doing some additional things say for the USGS, they want a soil model. That's not, as far as I know, that's not fundamentally the model that we're developing here. Is then.
I guess Norm's point is it's part of NGEs, but not the SHAC process.
Don't have, basically, we don't have two parts in NGA, SHAC versus non-SHAC NGA. Everything is SHAC. The nuclear industry obviously is interested in hard rock, horizontal ground motion, and so on. But we have a working group on geotech as well as a working group on vertical and so on. Everything is part of SHAC. Then if we accept that, because we don't have two parts in the project, then if we accept that the geotech, they're collecting data for the soil amplification basically. And then we have to hear from them that if they're doing it, what's the plan and is it complete or not complete?
Okay.
So you want me to talk about our plan for the data collection? Is that what you'd like to hear? Or
if you have identified issues or data needs outside of what you're collecting.
Our data needs is we actually are casting a wide net to collect data on rock velocities, but also soil profile velocities, and also soil modulus and damping curves, so that we can develop models that are then used in site response analyses. That's our plan. In terms of where we're trying to get this data from, we are engaging Ken Stokey. In fact, we have a meeting on December 2nd in Austin, Geotechnical Working Group, that will be focused on this issue. We have data coming from Bechtel. We have data coming from user Rutledge. We have data coming from DOE. We just had some discussions right now. And we just are keep on looking, and we had some discussions with several firms, some of them in this area. And we're in the process of seeing what they have and what they can release to us. But we've already gotten a data set from Bechtel, for example, and from user Rutledge is coming soon, very soon. So that's our plan for collecting the data, and by engaging someone like Ken Stokey, who has worked a lot on models for modulus reduction and damping curves, so we can have also his help with developing these models. So did I address the issue sufficiently, or are there questions on our plan for this?
I guess you're open to receiving more data, right?
We would love to get new data. Please send it to us. We are, all the data we can get, please send it. There's always an issue with the quality of the data. And so if you have data that you've, based on what I described, would be relevant to what we have, please send it to us. Or let us know. Or if you know of places where such data might reside, let us know so we can go out and try to get appropriate permission. It's really not a straightforward process. There are many issues and sensitivities that we have to go through to get the data, but I think it's working out okay. We've been successful. Thank you.
That's good. Youssef, that's good? Okay. Is there anything else we might have missed or not known should have been addressed? Bluntly honest here. Is there anything else that, from what Norm presented, the summary of today, that you don't think was captured in his summary that was discussed today? Okay, so I guess that's when we welcome comments more specifically from the PPRP if they want to, then the sponsors, and then the public. And we'll limit that to half an hour. And I guess we'll just finish early today. PPRP, you have comments you would like to make publicly, or you want to keep that for the closed-door meeting? Okay, so we'll have private comments from the PPRP. Thank you. I'm not sure it's good. I'm not sure it's good news. I don't like it. Okay. Does the JMC have comments or questions or require clarification from today's discussion overall? No? Okay. Yeah, okay. Okay, good. Thank you. So they've already asked their questions. So looks like everybody wants to go early, but is there any questions or comments from the general public, the observers today, who were not maybe allowed to participate earlier? It's only day 2. We have 2 more of those. So I suggest we amp up the caffeine in the coffee for the next 2 days. No more comments? Okay. On this, we'll close the session today.